Welcome everyone. So this is our 122nd live stream geometry. We have two other people here with us so far. So today I'm going to do problems from a mock contest that was on the AOPS forum. It's called GOWACA. So GOWACA. I think it's like Geometry Olympiad without a cool acronym. It was created in 2021. And it looks pretty interesting. So I will share my screen. Here's the first problem I picked from it. So we have a triangle with in-center I, and we draw three different lines perpendicular to AI, BI, and CI. Let's do that. This is I, and let's draw the three midpoints. 1, 2, 3. So we do it through the midpoint of BC, perpendicular to AI. Maybe it's worth drawing the circumcircle, I don't know. So we could draw the midpoints of the arcs and then drop perpendiculars to them. So we have this, this, and this. And we drop some perpendiculars from each of the midpoints to the corresponding sides. So this, this, and this. And they form a triangle with orthocenter H. And we want to find the radical axis of ABC in that circle. So we have 1, 2, 3. And we want to show it bisects IH. So I didn't draw, I need to rename this. Call this P. But H would be, oh, it looks like I don't have an orthocenter here. Okay. So let me just say ALM4. So that's H right there. And basically we want to show the midpoint of IH has the same power with respect to both circles. That's an equivalent way of saying it. All right, so what did I just do? Okay, let's do this. So we have 1, whoops, draw the midpoints of these arcs. 1, 2, 3. Then I'm going to basically hide all the lines and draw them in as segments. So we have this, this, and this. Then we also have this, this, and this. A little tricky of a figure. Let's see if I can make it look better. I think that looks okay.
It looks like, for example, KH and G are collinear.
Okay. KH.
So, and on the other ones as well.
All right. So P is like So G is like the foot of the altitude from K to LM. That's interesting. It's really interesting. So basically, I mean, MP is parallel to BO, CQ is parallel to LJ, right? So we have all these parallel lines. Maybe we can use that to try to prove it. Yeah, basically it's saying, yeah, that's interesting. C, um, so yeah, that's the first question. If we take a general triangle ABC and we draw the three midpoints of the sides and we take parallels to the angle bisectors, is it obvious that those should concur? So triangle GPJ is the medial triangle. I think it, so if we draw this medial triangle, GH is not like the angle bisector. Maybe it is. Oh yeah, it's true. So H is going to be, we could define H to be like the incenter of GPJ. And then we'd have to show the other stuff is true. So that's one way to think about it. Okay, so what if we do that? What if we redefine H, we could call it H prime to be the incenter of the medial triangle, and we see where GH prime, PH prime, and JH prime meet. Yeah, I'm not sure what this circle would be, that's the only thing. But if H is the incenter of this, then I think you can kind of always construct, like if you take the incenter of any triangle and you draw the perpendiculars through the vertices, I think you probably always get let me think about that. Basically, then I think H prime would be the orthocenter of the new triangle. So I think that might prove a lot of this. So like, for example, if I took triangle ABC and I drew perpendiculars to A through AI, B through BI, and C through CI, then would it be true that I is the orthocenter of that new triangle? I think it would be, right? Let's check it. But I think that's just true in general, and I don't think that would be that hard to prove. Yes. So basically, Yeah, because then I think then L like M would be the X center, the PX center of JPG, and L would be the JX center because we're taking the two perpendiculars. Looks like Dhruva is trying to join. Let's see. Looks like Serdar is joining. Hey, Dhruva, thanks for joining. And Serdar. He should be hopping on any second. Hey, Dhruva. Hey, Serdar, thanks for joining. So this is our first problem. And we've made some progress on it. But yeah, I think it's safe to assume that, yeah, we can assume like K, H, and G are collinear, M, H, and P, and L, H, and J. I think we can prove that using kind of what I just said. So that's not given in the problem, but yeah, I don't think it's hard to prove. Oh, did we try this before? I don't remember. It's possible. Yeah, there's some things that there's some things that I've done twice, to be honest. But do you remember this problem, or do you remember the solution?
I don't remember the solution, but I remember the problem.
Let's see if we can figure it out again. Okay, so we want to show the midpoint of IH has the same power with respect to both circles. So H is the orthocenter of KLM. I wonder if I is the incenter. That would be very interesting. No, that's not true. Maybe we could use Casey's theorem. My parents are talking in the background. Do you guys hear them?
No, I don't hear.
Okay. Let's see. So yeah, with all these parallel lines, like AG is parallel, KG is parallel to AN, BO is parallel to PM, and CO is parallel to JL. Makes me think of like parallelograms. So I mean, basically, like the midpoint of IH would be the center of like 3 different parallelograms.
Well, QON and KML, they are similar triangles, and also they must be congruent. So we need to prove that, yeah, they're equivalent. So we need to prove that OQ equals to ML to finish the problem.
That's a really good idea. Obviously, AQIO is a kite by the in-center off-center lemma. And for ML, so yeah, basically these two circles are the same size because they surround congruent triangles. And I is the orthocenter of one and H is the orthocenter of the other. Yeah, we know the sides are mutually parallel because QO is perpendicular to AI, since AQIO is a kite. And ML is perpendicular to AI because it's perpendicular to KG, which is parallel to AI. Well, I know, actually by definition, ML is perpendicular to AI. So yeah, we know the sides are mutually parallel, but we just have to show they are the same length.
The KL is Simpson line of O, and KM is Simpson line of Q.
Okay.
So it can be good to intersect KL and KM with BC.
Okay, KL and KN with AC.
BC, KL and KM.
Okay. So we have this point. Oops. R. And then we have a point S. Sorry. Okay, so you said we have a Simpson line, so
So QR and OS are perpendicular to BC.
okay. So OP so it's not necessarily true that OP and G are linear, right? But OP is perpendicular to AC because it's the midpoint of the arc, and P is the midpoint of AC. Okay. How do we know that, or do you know that OS, or were you able to prove that OS is perpendicular to BC?
Well, the Simpson line of O is perpendicular to BI. We can easily prove that.
Okay.
And OP is perpendicular to AC, so it passes through P.
Okay. So this is a Simpson line. And it's also a known fact that the Simpson line bisects the segment connecting O to the orthocenter, okay, which would be
Well, orthocenter of ABC is not on the diagram.
oh yeah, you're right. So yeah, that's probably not that helpful. Okay, so we want to show QO equals ML. That's our goal here. There's like another way to do this. So H is the incenter of GPJ. Let me draw this point and point down to AI. Oh, I think I've solved it. So basically triangle GPJ is similar to ABC because it's the medial triangle, right? And H is the incenter of GPJ. So GH has to be half of AI, which is TI. So TI is equal to HG. And at the same time, we know that triangles NOQ and AML are similar. And so if and segment IT and TI in one of them corresponds to segment HG in the other, so they have to be congruent. I think that works, right?
Yeah.
Okay. All right, so I'm going to write it up. I'm just going to delete S. Whoops. Sorry. But that's an interesting idea. Okay. So first, basically, the problem never says that KH and G are collinear. But I think it's true because, yeah, because K is the GX center of GPJ. So, and H is the N center. So it would have to be that those are collinear. So, I'll say redefine H. Let GPJ be the medial triangle of ABC. And then redefine H to be the incenter of GPJ. And then because of these perpendiculars, so I mean by homophily GH is parallel to AI. GH is parallel to AI, and then PH is parallel to BI. BI and JH is parallel to CI. And those, all three of those together. Okay, so also K is the GX center of GPJ. And that implies that KH and G are collinear. Same for other sides. And this means that KH corresponds to the original definition. That's the first step. Okay. And then also triangle KLM is, I'll say, and triangle KLM is similar to QON. So we know those are similar. Now we have to show they're congruent. But HG is going to be half of AI, which is TI. And that's because since AQIO is a kite by the in-center external lemma. And so these two, so since HG equals TI, then that means that we actually have KLM is congruent to QON. With H corresponding to I, or I corresponding to H. Dang it. See if that's right. Or, sorry, H corresponding to I. So I mixed up the two. And that implies that, so by symmetry, the radical axis has to pass through IH. So that solves the problem. Has to pass through the midpoint of IH. Pass through the midpoint of IH. I mean, basically, the midpoint of any two corresponding points of these triangles has to lie on the radical axis. All right. So nice nice solution. So I will move on to the next one. Yeah, this problem, yeah, I think we might have done this before, but I don't remember it that well. So we have a triangle circumcenter O, orthocenter H, and we draw the altitude and the median. So let's see what I can do with that. Actually, let me, if we're going to draw the orthocenter, might as well draw all of them. So, looks like Serdar had to hop off. Okay. AM is the median. So, well, then we draw a line through H perpendicular to AM. We see where it meets AM and BC. Meets AM at P and BC at Q. And then OA and OD, we want to see where they meet the circle DOC. So this circle, like the tangents at B and C meet at the antipode of O. And we have, oh, we need to shrink the diagram. So we need to see where AO meets it again. So something more like that. We have OA and OD, and they meet it at T and R. S is the foot from A to TH. So is it this point right here? I think it is, right? Because AFHE has to be cyclic. No, actually, I got confused. It lies on that circle, but it's not on the circle ABC. Okay. We want to show that PQRS is cyclic. So we have this. This. All right. So is it true that EF and OD are parallel? I don't think that. Yeah, that's not true in general.
So there are two more points that appear to lie in a circle, PQRS. One of them is the intersection of TS with BC.
Okay.
And the other one is the intersection of AM with OD. And these 2 points, if we connect them, that line is also perpendicular to BC.
Interesting.
So the circle we want to show is the one with diameter QI.
Okay.
But I can't prove any of this.
That's pretty interesting though. There's diameter QI. Just gonna draw the circle just for the heck of it. So yeah, G and I are not hard to define. So I is the intersection of OD and AM. For QH and P collinear? Let's see. I think so.
By definition, yeah.
So Q is
Q is the X point and P is the Humpty point. But in the problem, it just says the line through H meets these two lines at P and Q, so they're all collinear.
okay. So yeah, by definition. Yeah, we know QPI is 90 degrees. Maybe we could define G as the foot of the perpendicular, and then we could try to show those are all collinear. So then we would know that QPIG is cyclic. We would have to, yeah, how did we define G? Oh, because originally we defined it as intersection. Okay. So yeah, we know that H, M, and this point are collinear. We want to show that H, G, and T would be collinear under this definition. Maybe we can add a little bit more, so. Let's see. EQRI. Let's see. So B, C, D, and Q are harmonic. It's true. Hey Khan, thanks for joining. So we're on the second problem here, and Panos has an idea. So B, C, D, and Q are harmonic, and we invert about the circumcircle, so D and R would swap. QR is the polar of D. Oh, well, it's all right. Thanks for joining us now. So this is the second problem. The first one was pretty interesting. Yeah. But yeah, this is the second. Okay, so QR is the polar of D. And ORQ equals IRQ equals IPQ equals 90. Okay. So let me think about that PQRI. So let me hide the circle for the time being. So, okay, so first of all, you're saying D and R swap.
Because BC goes to the circle of BC.
Okay, because BC goes to the circle BOC. Okay. I guess another way to think about it is like DRO is angle bisector, BRC, so then we have similar triangles, but yeah, it's the same. That's the same place. Okay. So QR is the polar of D because we know R lies on the polar of D by that inversion, and Q lies on the polar of D. Sorry if that's obvious, but why is that true? Oh, because that's true if D lies on the polar of Q, and oh, because the harmonic. That's right. Okay, so QR is the polar of D, so QR has to be perpendicular to IB. And then we kind of defined QPI to be perpendicular. So that would prove that, yeah, QPIR is cyclic. So then it would just remain to prove S lies on it. But yeah, so
It would suffice to show that SHA and SRI are similar,
okay.
and that appears to be true.
So SHA and SRI. Basically, let's see. But SHA is a right triangle, right? Does that mean SIR is also a right triangle?
Yeah, that's what we want to show, right? We want to show that R lies on the circle with diameter R. S lies on the circle with diameter Ri.
I think QI, right?
Yeah, QI. Sorry.
Right. So are you saying AHS and SQI
Wait.
should be similar?
Probably, yeah. 1 second.
Sorry.
Yeah, that's what I meant.
Okay.
Also, and I don't know how helpful this is going to be, but SHDR appears to be cyclic.
Okay. It's interesting. And maybe we could prove that because it may looks like those concur. But yeah, we'd have to show that R lies on that circle. Okay, so if this is a right angle right here, maybe we should draw this point, because then that means this is the antipode of O. And so LO and M are collinear, and we would have a couple things. LB and LC would be tangent. So yeah, T is defined in an interesting way. So yeah, we have to figure out how to use that.
There's a lemma, and I don't know if it has a name, but it states basically T is the what we get when we use root BC inversion on H. And actually, the more general lemma is like if you take a point P and like any point, and you you intersect AP with PBC, with the circle PBC. Okay, well, not that point P. Well,
But
that's
yeah,
the
I get what you're
same.
saying. Yeah, so you draw, you draw like the circle PBC or whatever point, and then you'd intersect it with a circle.
Yeah, and then you get the same point as when you just take the isogonal conjugate of P and do root BC inversion on it.
Interesting.
And in this case, like O, the isogonal conjugate is H, so H and T are inverses under root BC inversion.
Okay. So AH times AT is AB times AC. So triangles ABH and ATC are similar. Oh yeah, and yeah, that's easy to prove directly too. Yeah, because like angle CAT is BAH, and angle CTA is CTO, which is CBO, which is ABH. So yeah, these triangles are similar. So yeah, that
Yeah, that's the proof.
yeah. Okay. Okay, so we can think of T like that. So under that root BC inversion, do we want to see where S would go? So T and H would swap. So the line TH, yeah, I'm not sure where that would go.
Well, TH would become the circle ATH, and
Oh yeah,
the circle with diameter AH would just become the perpendicular to AT through T.
okay. So it would be this that line. So basically line LT. So that means S would go to this point all the way off. S would go to this point right here. All right.
Yeah.
And okay, so if we look at QPI R, see if there's anything special about this point. Looks like it passes through that. The H and T get swapped. Where would P go? So AL is the median. So P would go to some point on AL. So would I. I wonder if these look like they can curve. So it looks like the circle we want to prove, yeah, and this circle like intersect on this median.
Is it true that we just need to prove, like we can delete point S and just prove that IGRQ is cyclic?
We've actually already proven that or PQRI is cyclic. Oh, but you're saying G.
Yeah. Because like I think, oh wait, hold on.
Okay.
Yeah, did you guys prove that QRGI is cyclic?
We proved that PQRI is cyclic, but we didn't prove that G lies on it. I guess it depends how you define G. But if you define G as like where this intersects BC, then we don't know that G lies on a circle. Yeah, V would be like another point that lies on a circle. Oh, 1 sec, I'll be right back.
But we haven't proven anything about S. So, or like, how do you want to restate the problem? Exactly.
It's like you can delete point S because we can see that we have HS times HG is equal to HA times HD, and it is equal to HP times HQ. So we have SPGQ is cyclic.
Okay. Sorry, I just got back. So SPGQ is cyclic. Okay.
So that's why we need to prove that QPGR is cyclic in order to prove the original problem.
Okay.
So yeah, I mean that we can just delete point S and we define G as the intersection of TH and BC.
Okay.
And then we need to prove that PGRQ is cyclic.
All right. So let's hide a bunch of things for now.
I mean, we don't necessarily do that, but yeah, it will make things like less complicated.
Yeah. So G is the intersection of TH with BC. Okay. And yeah, so I think it might not be that hard to yeah, prove that IG is parallel to AH.
But we can choose any point among like PQRI that we want to ignore, right? Like we need three out of those and G to be cyclic.
Yeah.
So which one do we want to ignore? I think we might want to ignore R maybe, because then we can do we have like PI and QG intersect at M. And we could also ignore P, but P is the Humpty point. That would be like a little bit weird to just ignore it, because then we'd have the intersection at D.
Mm-hmm. So yeah, so for PQIR, we could pick 3 of those, and we want to show they're cyclic with G, is what you're saying. And
Yeah.
it's just a question of which one. But yeah, if we could show
Right,
IG
so-
is perpendicular to BC, that would be good enough, right?
So which one do you guys prove cyclic?
PQRI
already
we showed
proven.
was cyclic.
You guys already done that?
Yeah,
Yeah,
we
that
did
was
that. So the
Yeah,
proof
so
was
how do you
that.
do it?
Sorry, what?
How do you guys prove PQRI cyclic?
So Panos actually proved it. So first, Q lies on the polar of D. So BCDQ is harmonic. So Q lies on the polar of D with respect to ABC. And then R also lies on the polar of D because if you do an inversion with, I'm trying to, like, I think the radius is like OB, then yeah, then BC goes to the circle BOC, so D goes to R.
I got it.
Okay.
So yeah, can you continue?
Sure. So yeah, so since this is the polar of D, then angle QRI equals 90, and angle QPI is 90, because P is the Humpty point. So yeah, QPIR is cyclic.
Nice. Thank you.
Yeah, you're welcome. So we want to show that AI over IM is DG over GM, right? And AI over IM, like that's AD over OM. So yeah, I don't know. I'm just thinking here. Yeah, if we could show IG's parallel to AD, that solves it. So we can really hide a lot of stuff. Let's see something. You want me to hide like a whole bunch of? Yeah, let me get. I want to try to do it that way if I can. So let's hide all this. Yeah, all we really need is IG. Yeah. Actually, let me just select a whole bunch of stuff at once and hide it. Oh, I think if you hold down Control, yeah, you can select as much as you want. Oops. Oh, we still need this circle. So let's see. Let me add this back in, or just OD. So yeah, we just want to show IG is parallel to BC. Or IG is parallel to AB. Maybe we could do it like this. So if I drop a perpendicular from J to BC, these are like symmetric. So I was thinking we could say like DM over GM is KM over GM. But yeah, I'm not sure where to go from there. Yeah, thanks for joining, Pascal. Yeah, this feels like, yeah, showing IG is perpendicular or parallel to AB or perpendicular to BC seems like it should be doable. So I wonder if we should try to do this. So this meets the circle at a point. So dg over gm would be like kw over wj. I don't know if there's anything special about w. Let's see. Maybe not. I mean, it's also the same as saying that AD over OM is DG over GM, I think, right? Which is the same as saying that those triangles are similar. I think that's right. Let me just check that. Yes. Yeah, we're really close, I feel like. So AD over OM, we want to show that's DG over GM. And then DG over DH, like maybe we could drop a perpendicular from T to BC. DG my brain is not working. Let's see. So OM is half of AH. So let's try that. So AD over OM is, or OM over AD is AK over AD. So we want to show AK over AD is GM over DG. Or GM over DG. Yeah, so we kind of transform the problem, that's the thing. Oh, sorry. Let me first. So is T the AX center of, is A the TX center of TBC? Let's see. Looks like, yeah, maybe J is the end center of TBC. So let's see. We take the, yes, it looks like that's the case. Okay, so it looks like J is the end center and A is the X center of TBC. Let's think about that. So, like, this has to be an angle bisector because, yeah, O is the midpoint of arc BC. And yeah, then by the in center X center lemma or something. Let's think about it. How do we know that this is the in center? It has to be because OB equals OC equals OJ. Okay, so that should help. But Pascal. So we started with one problem, but we turned it into a new problem. So basically, we're just saying if OD and AM intersect at I, and TH and BC intersect at G, then we'd have to prove that IG is perpendicular to BC. So yeah, that's the new problem. Which I think is the same as saying KG is parallel. Yeah, is that the same as saying KG is parallel to AM? Maybe I'm confused. No, because it would be AK over AD versus GM over GD. So that would not be true. All right, let's spend like another 10 minutes on this, or yeah, I don't know why it doesn't look that hard, but somehow I'm getting stuck. Yeah, mg over dg. That's just key ratio here. I just don't see how to get that. And maybe we could use projective geometry somehow. So if we project mgd in some other point, and yeah, these I think are collinear with that, right? H, M, J, and Z. So maybe we could project these onto this circle. So M goes to Z, D goes to A. The intersection of
I think that the problem is equivalent to proving that dmgw is harmonic.
oh really? Okay.
Yeah, because if you let G prime be the foot up perpendicular from I onto BC, then you will have dm G prime W is in harmonic conjugation
Okay.
because yeah, it is
Because these
I
are
G prime
parallel.
OM and AD are concurrent at infinity point.
Yeah.
So yeah, what's left is to prove that dmgw is harmonic.
Okay. I like that. So let's think. We could try to project through T, or maybe project through project through O onto the circle.
Oh yeah, so we are done. I think we project to H.
Okay.
So we have HD, HM, HG, HW. We project it onto the line AO.
Okay.
So D goes to A, G goes to T, M goes to J, and W remain the same, which means that we can easily see that this is a harmonic conjugation because earlier we said that A is the excenter
Eccentric.
of TBC. Yeah, so
That's
yeah,
really
the problem
nice.
is pretty much.
All right, that's really nice. Okay, so basically, yeah. So if these are harmonic, then IG has to be parallel because sorry, I'm trying to remember. So if these were harmonic, then because these two are parallel, that proves that IG has to be parallel. Why is that? Okay.
So you can let G prime be the foot of perpendicular from I onto BC.
Mm-hmm.
So how do I say this? Can you draw a line WI?
Yes. Oops, sorry.
And I think you have to draw a WI. Then you let WI intersect OM and AD at a 2 point. Yeah, A1 and B1. So we see that WI A1 B1 is a harmonic, right?
Oh yeah, and then you
And
just
since
project it parallel to AD, and
yeah,
you get that those
exactly.
are harmonic.
Yeah,
Uh,
like you can explain it either way. Like it's just left to prove that DMGW is harmonic.
Interesting. All right. So, all right. So I'm going to add some of the other points back in. I don't think I need. Okay. So let's see. So we have S. Yeah, I'm just going to hide that circle for now. R, Q. So EF is not originally there, but I'll just leave it for now. It's not hard to prove. Okay. So first, we know that BD, BCDQ is harmonic, like Pano said. So that means that Q lies on the polar D. And also R lies on the polar D because by inverting about the circle centered at O with radius OB equals it, or I'll just say by inverting about the circumcircle. B inverts to R. Since BC, BOC, and that implies that DR or QR is the polar B. And that means that angle QRI is 90. So I is actually not defined in the problem, so I'll put that. Okay, so let AM meet OD at I. And let TS, or let TS intersect BC at G. Okay. What was I doing? Okay, so first we use power of a point to show that. Okay, so this means that QPIR is cyclic. That. We also know, I think it was at QSPG is cyclic, right? Because QH times PH is AH times HD. Which is which is SH times HG. And so QSPG is cyclic. And then we could try to show IG. Okay, so T is the in-center of so O lies on, first of all, O lies on the angle by OB equals OC. Means that O lies on the angle bisector of BTC. And then by the in-center, x-center lemma, J is the in-center and A is the x-center. Or J is the in-center. And A is the T x-center. And that means that we have a harmonic conjugation. So that means that TOWA is harmonic. And then we can project that through H. I think it was H, right? Not O, TWJA, I think it should be. And then we can project those through H. Okay. So projecting through H onto BC, then we get
I think it's W, not K.
okay.
Yeah.
W.
Yeah, you just type.
Yeah, you're right. So then we would get GWMD. Projecting through H onto BC. And this implies that IG is parallel to AD. That's from the argument you just said. So yeah, it took me a while to think about it, but I actually think it's obvious. I think I was just kind of slow about thinking about it, so I'm just going to leave it like that. So once we know that, so I mean that means IG is perpendicular to BC. That means that QPIGR is cyclic. And then S is cyclic. And which solves the problem. All right, so we can move on to the next one. So yeah, that was a good solution. All right, so let's see who. See, I think Johannes had to hop off.